Missy's golden All right. The topic for today, the real topic for today, is chaos. Wow. Whoa. But in order to introduce the feeling of chaos, we're going to do something different first, just to so it feels a little chaotic.
Just not another bifurcation.
Right. Well, it's not another bifurcation, but it's another instability. All right. There's something in life that's called a parametric resonance.
Okay.
All right. What is this? Every child of the age of 6 knows what this is, because that's how swings work. Right? You're sitting on a swing, and what do? You know, when you're 2 years old, your parent sits there and pushes, right? That's just driving, right? That's external driving, and that's very nice, but that's not the issue, right? When you're already 8, you know how to do this by yourself, right? If you would just, so right. First of all, you run backwards,
right?
and so you give yourself a little initial velocity, right? But quickly friction sets in, and you go. So you have to pump it in order to keep it moving, right? Because that's the whole fun of life, is to keep it moving. And how do you do that? You move your legs, right? When you're at here, your legs are extended, are folded back, right? This is your knee, and this is your foot. And then when you're here, you're fully extended, and then when you're here again, your knees are tucked in.
Okay.
Right? Right? You're here. This is your knee again, and this is your foot. Right? And that's the way, and here's your knee. Right? That's the way it works. Right? In other words, you're changing the moment of inertia of this thing. Right? Because when your knees are folded up, your moment of inertia is less. And when your knees are extended, when your legs are extended, your moment of inertia is greater. Right? And you're doing this, how often for each swing, right? A swing is up here, through here, and back. How many times do you change your moment of inertia? You change it twice. Right? So you change the moment of inertia twice as often as you change it twice per period. So, and there's a deep reason for that, right? Which is called parametric resonance. So we're going to talk about that. It's like the resonance we saw for the Van der Pol oscillator. This is also an oscillator. The only difference is, so the equation is, right, the linear equation, we'll just worry about the linear equation for the moment, is minus x 1 plus epsilon sine t omega minus epsilon gamma x dot. So here's some friction, because there's friction in the system, right? And this is the fact that the natural frequency is not just 1, right? The natural frequency has to do with the moment of inertia, if we remember, right? It's because it's something like mg over L or something, so it has mg over I, generally speaking, it's like g over I or something like that, is what sits there, right? You have to think about this, right? The question is, how do you get a frequency, right? We need an omega, which is a 1 over time from, we have g, which gives us length over time squared, right? This is length over time squared. And then we take, so we take an m here, and that gives us a mass, and then here we take an I, and something like that.
You need L squared.
Right, L squared, right. So you need mgl over I, or something, because that gives us length squared.
And square I is kilogram times.
This is ml squared.
Yeah.
Right.
So you need
something like mgl over I, or something like that.
This is omega squared.
This is omega squared, right?
You write omega twice.
Whatever.
Okay.
The point is that changing your moment of inertia changes the frequency of the natural frequency of the pendulum, right? So what you're doing by moving your legs is changing. This is what, so omega squared here is a function of time, right? Omega squared is 1 plus epsilon sine t omega, where t is, that's the question, is what is t? This is now, this is omega naught, and this is the pumping frequency of your legs, and we're going to see that it's 2 to get resonance. All right?
It's supposed to be multiplied by a constant, right?
What's supposed to be multiplied by a constant? Times, yeah. There's the omega naught squared, which is 1, right?
Yeah, every time.
Of course it's 1, because what other units would you ever choose, right? Okay, so what do? We do the same thing we did for our friend, the van der Pol oscillator, right? What did we look at? We looked at the change in energy, right? We looked at the change in energy. So the change in energy is, right, it's the EDT is x dot times x dotium plus x, right? Something like that. That's the change in energy, because the energy is x dot squared plus 1/2 x dot squared plus 1/2 x squared. So that's the change in energy, the rate of change in energy. And now this is x dot times x dot. There's a minus, of course, here, because, of course, there's a minus there. And therefore, what you get is minus epsilon sine omega t, right? Minus epsilon gamma x dot. Right? Okay. And now we assume, again, that x is some slowly varying thing, a times cosine t, because the unperturbed, right, without epsilon, it's just the natural frequency is 1. So therefore the solution is cosine t. So we write that x is a of t times cosine t, right? And we assume that a is slowly varying, so we don't have to worry about it. And then we plug that into this. And so we get that x dot is minus a sine t. Right? And here we get minus epsilon sine omega t. Right? And here we get minus epsilon gamma times x dot, which is plus a times, there's an x here, right? Yes, of course there's an x here, because there was an x here. Yes, there was an x here. So that x is a cosine omega t, cosine t, sorry. And this is epsilon gamma a sine t. Okay. All right. So now we want the average of these. We have to look at the average of this over a period. So the last term is the same kind of term we always had. It's the average of sine squared. It's a half. Right. So that's fine. And that gives us some energy input. Actually, an energy decrease, because we have a minus line here, because that's friction. This term, we have a sine t, a cosine t. A sine t times cosine t is a sine 2t, up to factors of 2. Right? So this is sine 2t times sine omega t, right?
0.
I don't think that's supposed to be
The
that
average
there.
is 0.
What?
I don't think that's supposed to be the a cosine t there. I'm pretty sure the x cancels out. You have minus x and then you do plus.
No.
Oh, we have the
We
x
need
there.
an average. We need something that averages.
0.
Wait. Then okay. Am I being completely stupid, or what? What am I doing?
If omega equals to 1.
Right. No. So this is sine 2t. Right. What do we have here? This term, the first term, is plus a squared epsilon. Right. Sine 2t over 2, fine, times sine omega t. So now what value of omega is going to give you a finite average? There's only one value. 2. That is why parametric resonance happens when you pump it at a frequency, twice the frequency of the bare frequency. So that means you have to move your legs twice in every cycle, right? And that is parametric resonance. So that's now this is actually, I'm not supposed to talk about this in this course because I said at the very beginning, the first lecture, we're only going to talk about systems which are time independent, which are autonomous systems, right? And this is a system which is not autonomous because we're driving it in a time-dependent fashion. This is a time-dependent equation.
To solve it, we need perturbation theory, right?
Well, this is the beginning of doing perturbation theory, right? And then you do a little more and you can find out what the amplitude is, and the amplitude, right, will be the square root of epsilon type things and stuff like that. Actually, so you see, yes. So now when you have a balance, you have here, this thing averages, if omega is 2, right? Then if, and only if omega is 2, then this thing averages to a half, and we get this. And then we have the minus term, which is epsilon again, times gamma this is a squared, right? A squared times a half, because sine squared averages a half. So the point is that there's a critical value of
Wait, you wrote, you forgot the plus x.
What? No, I didn't.
No, never mind.
So there's a critical value of the friction. If the friction is greater than, in these units, a half, right, then it won't work. So there's a maximum friction that you're allowed in this system. Well, because we put the epsilon in here, i.e. the friction also has to be very weak. And the friction has to be such that this term is, less than half of that term in order for it to work. If there's too much friction, then the parametric resonance doesn't work. All right. So if your child is not, it's not working for him, take something and try to fix the friction. Oil the hinges.
Put the sling in the vacuum.
Right. That is also possible, but yes. It's also good for the kid because you won't hear him screaming then. Right? Okay, so that's, it's such an important concept of parametric resonance. It's one of the standard instabilities of life. And it's like a chaval not to, since we're already here and have the tools at our disposal to talk about it. All right. And you can do much fancier things, and if we had another 4 weeks, we might do fancier things. Oh, one cute thing that I only learned about 6 months ago, is the following: that here, you can talk about this problem quantum mechanically, which is very cute. If you have a harmonic oscillator, real quantum harmonic oscillator, Schrodinger's equation and everything, right? And so everything we're doing so far has been really classical, right? It's stuff that, Newton could have gotten into and stuff, right? But here, you can take a quantum oscillator, and what you can do is change its frequency, right? You can build like a Josephson junction, which is a quantum oscillator, and you can have a diode, which is some kind of magnetic field. And if you switch the field, you can change the frequency. So if you now take your Josephson junction and have the frequency be changed periodically, you can pump the system. So how does that work? Right? Because all these equations have nothing to do with any of that, right? So or at least it doesn't look like it has anything to do with any of that, but it really does. So the way you can do this problem, we won't do it here again, but it's a really nice problem, and it's actually you can take a harmonic oscillator, and so you know that, and you expand it in eigenstates, right? You extend the harmonic, right? You have psi, you want to have psi of t, and what you do instead of having the the natural frequency of the harmonic oscillator, the omega squared, and the harmonic oscillator change like a sine, you can have it change like a sawtooth, right? Every t seconds, you just change the frequency. So you have omega 1 and omega 2, right? Now you can solve the problem for a harmonic oscillator with omega 1. You can solve the time-dependent problem because you know all the eigenstates. And so the full solution is the sum over all eigenstates, each with an e to the I minus I 8 E nt over h bar or whatever it is, right? So you know exactly what the wave function is, right? Well, as long because you're keeping the frequency the same. So it's the problem you solved in first year quantum mechanics, right? And now you change instantaneously the frequency, and okay, all you have to do is change basis states. Because you don't know how to solve the problem, now the basis states, the eigenstates of the Hamiltonian are different because they have a different frequency. And omega appears in all the formulas for all the eigenstates. But yet you can take those bases, project them on the new basis, because there's in the omega 2 basis, right? That gives you an initial condition. You can propagate that wave function for another time t, right? And now you can compare the system at the end to the system at the beginning, and what you find out is then you have to trans back to the original basis at the end, right? And all that's happened to the system is it's gone through some linear transformation. If you had an initial wave function of alpha ak, right? You can now you'll see that after time 2, switching the frequency and switching it back, it goes to AK prime. And so you have a matrix. Well, actually, there's a matrix. So it's it's some matrix times AK.
Right.
Right? It's a linear problem because quantum mechanics is linear. So this is a perfectly linear problem. And then you ask the question what are the eigenstates of that matrix? And the eigenvalues of that matrix are called Floquet indices. Because this is a time-dependent quantum mechanics problem. When you have time-dependent, they're like the block states in space when you have spatially periodic systems. Here you have a time periodic system, so you get the time-dependent equivalent of a block wave number, which is called the Floquet index. And then you look at what those spectrum of Floquet indices are, and you can then track how the energy of the system changes as a function of time, and you'll see that the energy grows exponentially, which is the exact same phenomenon here, as long as you change as long as the omega pumping is 2, twice the bare frequency. And I never thought about quantum mechanics in the context of dynamical systems, but in fact, you can actually now take this to your quantum mechanics class and tell them that you're doing quantum mechanics. All right. Okay, so now we're done. That was just a little excursus, and now we're back to chaos.
First meeting the creature.
So, this lecture is all about the work of basically one man, and it's basically the work of one paper, because there's a man who invented the whole field, and his name is Lawrence.
The same one from...
Not the transformations, who's a Dutch guy. This is an American guy. He was at MIT in the 1960s. He was a meteorologist. In what they called it something, they called it, what was the department called? But basically meteorology. It was the...
Climate physics.
What?
Or something like that.
Yeah, well, they had
Geophysics.
at MIT they had their own building, atmospheric sciences or something. They had some fancy title. Well, basically, he was a meteorologist. Yeah, studying weather. No. No, but when he did this work, he was at MIT. Pretty sure.
Did he got a Nobel Prize for it?
No. So anyway, what he was trying to do is write down a simple set of equations for modeling the atmosphere. And we're not going to worry about what those equations mean. I mean, the Strogatz actually tries to explain make you feel like you understand the equations, which you don't. So there's no point. We don't have any of the background we need to really understand the equations. I don't have the background we need to understand the equations. So we're going to forget where the equations come from, but he wrote down some set of equations. And the equations were the Lorentz equations, a three-variable system. And they read as follows. Don't blame me for the notation because it's his notation. Right? He wrote down these system of equations, and it really doesn't matter that why he wrote them down. What?
Too much modifications.
Well, no, it's actually very simple. There is a bifurcation.
Close to me.
Right?
Want to be.
So, right, and now, so okay, we can now go through the analysis, and we will in a minute but then they have to look at the pictures because the pictures are everything here. So
There is explanation with foxes to this equation.
no, well, there's an explanation not of foxes, but of motion of the air and the convection and of heat in the atmosphere, blah, 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 right? I mean, can't you see that?
Yeah, sigma is a sigma.
No, and Strogat says that sigma is like the Prandtl number, and R is the Reynolds number, and, well, B, he doesn't know what that is. Has to do with
It's a beautiful number.
Right. So, what he did, anyway, this is already in the 1960s, there were computers at MIT. Right? Because MIT, right? I mean, there was even when did Weizsäck start? Late in the early 70s or something, right? There's something like that. Yeah, the Weizmann computer. The first Weizmann computer. The first computer in Israel was built at the Weizmann Institute. You don't know this? Don't they teach you anything in school?
School. We barely know how to solve ODEs.
That was the first computer in Israel. Because there was other computers with the name AC, which I now have forgotten because I'm getting senile. But the WEIZ stood for Weizmann, and I think they still have it. If you go to the Machon and you ask nicely, I think in their computer science building they actually have at least a piece of this. So
It's not work.
what?
It's not work. Today it's not work.
No, it doesn't work. It's not working, but you can see, a piece of it, right? And so, okay. Anyway, so MIT, there were computers by then, an IBM 360 or whatever, some, thing that cost $1 million, and he said, he wrote himself a differential equation solver, like ODE 4.5 or something like that. There was no MATLAB back then, of course, so he had to write his own. But that's okay. It's not so hard. And he just simulated it. And he discovered the most bizarre behavior that he could imagine. This is what he saw. Right? This is y of t. So, okay, he started, and as we'll see, he started getting oscillations. That's nice.
How did you know that it is really described in nature?
He didn't.
Sense?
He wrote the equations down and then said, well, what did they do?
Just guess.
Yeah.
This is y of t.
Nice.
Then why we're talking about x, y, and z.
Right. I will see the whole thing in a minute, but it would just
Okay.
para, right? So, no, the point is, so y, so there's this value of y corresponds to one of the fixed points, which we'll see in a minute. There's a fixed point, right? There's 3 fixed points. There's one at the origin, and then one at plus x equals y, and z equals some number, and then there's the minus x and y, and z is the same number, right? So this is one of the fixed points, right? And it's oscillating around the fixed point because the fixed point is unstable. All right, fine. And what does it look like? It looks like a Hopf bifurcation, right? It starts oscillating, right? Because the fixed point's unstable, and then it has the Hopf bifurcation, blah, 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 right? So and unfortunately, you would expect to go to a limit cycle. That's what he expected. And so it's growing. And so evidently it's not a forward Hopf bifurcation, it's a subcritical Hopf bifurcation, because, and then all of a sudden the amplitude gets so big that it says, the hell with this, I'm going to do something else. And it goes, right? And then goes and up and down, and then goes down, and then it oscillates 4 times, and then goes up and down, and then oscillates a few more times, and goes up and down, and no matter how long he ran it, it kept doing the same stupid things, but never doing the same thing. You know, the number of oscillations looked like a random number, right? Each period, you know, each time there's some number, you can plot the distribution of the number of oscillations between, right, and things like that. And it's like a random number, you know, this is some distribution, and there's no rhyme or reason. And then you look at it in 3-dimensional space, which was hard on a piece of paper, but and you get the following thing. This is a cut. This is X and Y.
The Lorentz attractor.
This is the Lorentz attractor. Why do we call it an attractor? Because it doesn't depend on the initial conditions. It goes to this. No matter, you know, if you, for a given set of parameters, this is what happens. Right? So this is a global attractor of the system, and it is like nothing you've ever seen. It's not a limit cycle. So therefore it has the fancy name of a strange attractor, because it's very strange, right? And it was so named by, no, I think Ruel and Ruel named it a strange attractor. But anyway, and it's actually a 3-dimensional object, so the only way, what you need to do is to solve the equations and then plot these curves, and then rotate them in 3-dimensional space, because there's really, it's got a 3-dimensional structure to it, which is hard to see. But so this is what he saw, and this is not the only stuff he saw, but this is like, you know, like he says, what the hell is going on? This is not, you know, who asked for this, right? I mean, so he spent the next, you know, year or something, you know, trying to figure out what the heck was happening. And okay, so let's start at the very beginning with the fixed points, just so that we'll the obligation of finding all the fixed points. Obviously, x equals y is clearly an obligation, because otherwise we don't get that equation. Let's look at the third equation. Z equals xy over b, but x equals y, so this is x squared over b. Right? And now we just have to look at the middle equation. Right? And what do we get? We get x times r minus z. So that's r minus x squared over b. Right? Minus y is, so that's also minus 1 equals 0. So the answers are either x equals 0,
But then everything.
and then everything is 0. But that's a fixed point. That's fine, right? If x and y are 0, this is all 0.
Yeah, if you
Or,
vacuum or something like that.
right? X squared equals x squared equals r minus 1. So x equals the square root of b times r minus 1. Right? Which means that this exists, this is a fixed point if r is bigger than 1. Right? So what it so in fact, we know what happened, right? Because before, when r is less than 1, there's only one fixed point. And when r is bigger than 1, there are 3 fixed points. Right? There is this guy plus this, because we have x equals plus minus that. There's the square root. Right? So there are 3 fixed points. So what is the bifurcation where you go from 1 fixed point to 3 fixed points?
Supercritical?
A pitchfork. We could be supercritical or subcritical.
Okay.
We'll see that, in fact, that depends on whether the x equals 0 is stable or not, which is the next question. If the x equals 0 solution is stable, it's a supercritical. And if the x equals 0 solution is unstable, it's a subcritical. So we will investigate that in just a second. All right? So we have to write down our Jacobian matrix, because we only know how to do one thing in life, which is write down Jacobian matrices. Right? And we get that this is minus sigma. This is plus sigma. This is 0. This is r minus z. Right? But so let's only look at the stability of the 0, 0, 0, 1. Right? Then we can throw out the nonlinear terms, and this is just R. This is -1, this is 0. Right? And then the last one is this term with this drop is quadratic, and you get 0, 0, minus b. All right? The eigenvalues are, well, this eigenvalue is what? Minus b. All right? Now we look at this matrix, and we get that
-1
the trace is -1 minus sigma, and the determinant is sigma times 1 minus r. Okay. And now, in fact, okay, you can show, so we have to look at the trace, that the discriminant, which is trace squared minus 4 determinant, right? That is the square root of, right? 1 plus sigma squared minus 4 sigma 1 minus r, right? Which we can write better because this is 1 plus 2 sigma plus sigma squared minus 4 sigma. So this equals the square root of 1 minus sigma squared plus 4 sigma r, right? So this thing is always positive, right? And therefore, the lambdas are always positive. And then the question is, we have to, is...
So it's unstable.
So, no, wait, just give us a second here. All right, so now what do we have? So it's lambda, these lambdas are minus the trace, that's 1 plus sigma, plus minus the square root over 2. Right? Okay? And now, so the question is this is a positive number? If, okay, and his question is this bigger than that or smaller than that? So when are they equal? And not surprisingly, they're going to be equal when r equals 1. Right? So when r equals, because, right? So the question is, we have 1 plus sigma greater than or less than whatever square root, which means that 1 plus sigma quantity squared is greater than or less than 1 minus sigma squared plus 4 sigma r. And now this is 1 plus sigma squared, this is 1 plus sigma squared, this is plus 2 sigma, and this is minus 2 sigma, that becomes 4 sigma is greater than or less than 4 sigma r. So the square root is, if r is less than 1, then this thing is bigger than that, and this is bigger than that, and this thing dominates, and it's stable for r less than 1. So exactly, this means it's a supercritical bifurcation. When r is less than 1, which is before the pitchfork, it's stable. And on the other side, remember, we have a stable here, and then we have an unstable here, and a stable and stable. That's a forward pitchfork bifurcation. So it's a forward pitchfork bifurcation.
It is what? Again?
What? It's a forward pitchfork.
Forward.
Right? It's a supercritical.
Yeah, the one that's good for hay.
Yeah. Right, exactly. Not the one that's broken and bent back. Okay. That you stab yourself with or something. Yeah, okay. So anyway, so the origin for r less than 1, that's boring. Life is boring. It's just a stable fixed point at the origin. R greater than 1, we have 2 stable fixed points, and these are perfectly good solutions that, right, with small amplitude, and then they get bigger in amplitude like a square root as you progress in R. Right? So far, so good. And then you have to investigate, right, the stability in general of these solutions. Now the algebra gets a little messy, and we don't want to waste your valuable time going through the exercise, but Mr. Strogatz went through the exercise. Actually, Mr. Lawrence went through the exercise. And he found out that for r greater than a critical value of r, which he called RH, H standing for
Critical.
Hop. Right? There's a hop bifurcation. Both these solutions are subject to a hop bifurcation at a critical value of r, which you can write down, and he did, and I hope I did too. What is the condition? Yes. R hop is the beautiful, lovely thing, just to show you why you don't want to do this algebra. See me do this algebra for you. That's R hop.
I believe.
Right. Yeah, it's just so beautiful, right?
Yeah, very intuitive.
Yeah. Okay, everybody can guess. Okay, so so the point is, then there's a hop bifurcation, and then that's exactly when where he was running this. So before the hop bifurcation, you get this, you have a stable fixed point. Like, okay, boring, right? But then, you track, and then all of a sudden, but beyond that, well, he was expecting to see a limit cycle of some kind. Maybe it's a very big limit cycle because it turns out to be subcritical, right? Which is what he saw at the beginning of that run, right? At the beginning of this run, he said that when he just saw this far, he said, okay, it's going to be a subcritical limit cycle, right? And it's going to get to be a big limit cycle, and then it's going to stop. It'll saturate somewhere. It has to saturate somewhere. Or it'll go off to infinity, maybe. And the answer is no, and decided to do this. All right. There are a couple other features of this problem which are noteworthy. Okay, so first of all, the pictures are pretty. Why are the pictures pretty? Because there's a symmetry in this problem, right? Which is if you take x and y and you map them to minus x minus y, it's the same equations. So that means that gives the pictures a little aesthetic pleasure to them that they otherwise wouldn't have. Right? So that's nice. There's another interesting feature that it's what's called contractive. What does contractive mean? That if I start out with a bunch of points, a bunch of initial conditions, and I run the system, I start out with a dense cloud of initial conditions, right? And they have a certain volume, like a sphere of initial conditions. And now I run it for 2 seconds, and now I look at where this cloud is expanded to, or shrunk, and I calculate the new volume. Has the volume increased or decreased? Well, if the volume decreases, then it's called a contractive system because the volume that is taking up in phase space, or three-dimensional phase space here, is shrinking. How do you calculate that? Well, d volume dt is just the integral by Green's theorem or somebody's theorem like that. It's the integral of the divergence of the velocity. Right? That's because you calculate because you have a sphere of points and they're going outwards as a flux, and you go.
I think it's
Yes, right?
What?
Yes.
Yeah. This is dv, right? You start out with a volume integral. Look at how the envelope of the sphere, and then you change it to this thing, right? So now we can calculate del dot v from the equations, which I thankfully did not erase yet because I'm so brief. All right, what is del dot v? Del dot v is dv dx dot dx. Dx dot dx is minus sigma. Right? Then we have plus dy dot dy. That's minus 1. And then we have dz dot dz is minus b. Minus sigma, minus 1, minus b. Those are all negative things. Add them together, you still get a negative thing. So this is sigma plus 1 plus d minus v, volume. Because you integrate this constant over the volume, and you get the volume. Okay, so what does that mean? That the volume of its phase space is contracting exponentially, quickly. It's going, right? So you'd expect that there should be like a stable fixed point. That's good, because, right, you start out with a whole bunch of points that they all come back to a single point. That's what you expect from a contracting system. This is a contracting system, and yet the attractor looks like that. How does it manage to look like that? Because it has zero volume. It is infinitesimally thin. And it is this thing, right? It's not even a real thing. It's what they call a fractal, which, you know, if you ever heard what the word fractal is, which means it's a crazy object. It's not smooth. It's not anything. It's just that, and that's what it is. Okay, very nice. All right, and so now what do you
is a fractal? Fractal is something.
a fractal is something that, like, the simplest fractal is a Cantor set. You take the interval between 0 and 1, and you take out the middle third. Right? And now you take what's left, and you take the middle third of that out, which is, of course, smaller. And now you take each of the four pieces, you take the middle third out.
And what you get,
and what you get after an infinite number of times of doing this, besides a headache, is a fractal. It's got infinite many holes in it.
So how it is?
And the whole scale. Because the distance between each, you see each of these little lines, right? That sort of like, there's infinite numbers of, you know, in the full attractor, this attractor only measured for a time equals 100. If you would run it longer, it looks like it's filling in. But then if you blow up the picture, you see that there's still holes.
So
you run it for time of 1,000,000, and it looks like a solid object, but then you blow it up and you see that there's still holes. And no matter how long you run it for, there are always holes. And they have a scaling behavior.
So it's not really a line, it's just another thing like
it's
that.
not periodic, so it keeps filling in, right? But nevertheless, it doesn't fill in, because each of these lines is infinitesimally thin and whatever, and yeah.
So it's scaling variant.
Yeah, it has some scale invariance and stuff like that, and you can measure, talk about the fractal dimension of the attractors and all that stuff, which is not for us today to talk about. Okay. So what else can you do? So one other thing. So since it looks crazy and never repeats itself, so the next question he said, well, he actually noticed that if he changed, you know, maybe this was a problem of like the, you know, DT in his computer simulation. So he changed the DT. And it still looked like this, no matter what the DT he chose. But then he noticed that if he changed the initial condition by a part in 1,000, right, it started looking very similar. And then by the time you get to here, it's completely different. So the number of, you know, here there'll be 7 up, the 7 bounces before it does whatever it does. And it'll look completely different. And then you change it by another 10 to the minus 5th. And at the beginning it looks the same, and then down here, downstream, after some finite time, it's completely different. All right? That is the signal definition of chaos, which is sensitive dependence on initial conditions. Which is a strange way to talk about this, because all unstable systems have sensitive dependence on initial conditions. Anytime you have an instability, right? If I have an unstable fixed point, right? I move the initial condition by a small amount, of course, the difference grows exponentially, because everything is growing exponentially because it's unstable. So it's a more subtle kind of thing, because at long times, there's no dependence on initial conditions, because you get this, right? This is what happens at long times, independent of initial conditions. So at long times, it's completely independent of initial conditions. At short times, it's right, but the point is it's unstable everywhere. The idea is anywhere along this trajectory, you know, when you're, even though that this is, so here, you do the following experiment, which I actually reproduced I mean, because I didn't. So what I did is the following. Okay. And let me just get the pictures in the right order. They're beautiful pictures. Okay. So I started out with, I took from this well-developed object, I ran it for time 100 or something, and picked the last point on the. So I'm on the attractor, or very, very close to the attractor, right? And okay, I said I'm going to vary the initial condition by a part in 1,000. Right? I'm going to add 1,000, 0.001 times a random Gaussian random number to x, y, and z. All right? And I did that and then ran that thing. I did that 10,000 times. Right? And ran it for time equals 5. Right? And you see that that initial ball, which would be too small to see on this picture, has expanded to that. Right? Because all the points are fleeing, there's this exponential expansion of the initial uncertainty. Right? It's also been translated because I started, the initial point was here, there's a whole flow, but then around that average flow, there's been an expansion of uncertainty. Right? I did the same experiment, started at the same point, and now ran for time 7. This was time 5, this was time 7. The blue. Look what's happened already. It's spreading out everywhere. Right? Beautiful thing. Then you run for time equals 10, and you get this. Right? And by time 20, you've got the whole attractor back. So after time 20, the system has completely forgotten its initial condition.
How do you define forgotten?
Look at it. It's spread all over the attractor. So all these points 20 seconds ago were the same to within 1/10%.
I asked, how do you define
Stop being a mathematician.
forgottenness of the...
We define a metric which you call.
Well, so you can. Well, that brings us to the next point.
Okay.
All right. Which is involved with your question.
יש אתה יכול להראות את התמונה של זה המלא שוב?
Which time?
הכי מאוחר.
הכי מאוחר.
זה.
The one that's a mask. Yeah.
יש
Right?
איזושהי דרך למצוא כאילו את הקצוות של הדבר הזה?
Well, there's no strict boundary, right? Because it's a fractal. It has a fractal boundary too, right? There's no line that.
Stop. How do you choose the points?
I had I took one initial condition, and then added 0.001 times a Gaussian random number to x, y, z. Right, and just followed it. I did this about 10,000 times because I have a computer, right? And that's what this is, the 10,000 points. Right? They all started out in a little dot that's too small to see. No, this is just the dots because each run gives me the end point.
So
at time 20.
Solve the ODE.
Solve the ODE 10,000 different times. Took all of 2 seconds. And I went out and got a Coke while I was running. Okay. So you can quantify this dependence on initial condition by doing this experiment. Right? You start out with a little cloud of points, right? And then you wait some time, and you see that it's gotten bigger. And you wait a little longer. Okay, but you don't want to wait a little longer. In fact, what you want to do is, all right, because so what happens is if you look at the distance, the average distance from the initial, from the initial condition, the original initial condition to any given point, right? So let's just say I start with a pair of points and watch how they spread, right? If I just take 2 points instead of 10,000, right? They're both going to move together, right? But they're going to spread a little bit. And I can measure how far apart they are from each other, right? So I can measure the distance as a function of time. And what you find out is that this grows exponentially. E to the something t, as long as, right, initially, right? Initially, eventually the distance saturates because the attractor has a finite size. So you can't get too far, right? The largest distance you can get is the distance from here to here or something, right? So it has to saturate. And but initially, if you start out with them 10, you set the precision on your simulator to be, very good. Start out with a distance of 10 to the minus 4 and wait till the distance becomes 10 to the minus 3. And you can pull it, just wait a second. I'll get it. Right? You see how long it takes to go from a distance of 10 to the minus 4 to a distance of 10 to the minus 3. Right? And that gives you a growth exponent. That exponent has a name, and then I'll answer your question, that's called a Lyapunov exponent.
All these names.
He's a Russian.
Yeah.
Lyapunov. So somebody here could say it better than me. Yeah.
So, on the one hand, you say that those equations describe something with climate physics.
Right.
Yeah.
Yeah.
And we know climate is close to be predictable for a term of a week.
That's right. Why?
That sounds to me
No,
long time.
that's no. Well, that's a question of what the Lyapunov exponent is, right?
Mm-hmm.
And so the Lyapunov exponent is such that it's something on the order of 2 weeks or something for the real climate. Because I mean,
And
so
what
that
we're measuring, we can measure the temperature for 2 weeks.
no, but the problem is that you have a computer, sitting somewhere in Washington and somewhere in London and somewhere in Moscow, or some giant supercomputer whose job it is to predict the weather. Right? They take all these measurements from thousands of stations all around the Earth, measuring the temperature, the air pressure, the humidity, blah blah blah, whatever they can measure, right? Which is nowhere near enough measurements, but that's what they have, so that's what they use. They feed this into their computer, right? They run it and they then they want to see what the weather is going to look like tomorrow. Except that if you change any of those input data by a small amount, of course, the answer will change. So if you run the program for a day, asking what the weather will be tomorrow, you'll say that there's a 10% variation in what's going to happen. Right? It's actually much worse than that because what do they tell you? It's going to rain today with a probability of 20%. That's the best they can do, right? I mean, come on, because it's a problem because they know it's going to eat because they tell you information which is what you want to know, but it's not all they can tell you. Because what they really know is it's going to rain somewhere around Rehovot, right? But unless it's a big storm, it might rain in Rehovot, it might rain in Rishon, it might rain in Ness Ziona. They have no idea whatsoever, because their spatial resolution is like I have one grid point for the state of Israel, right? I mean, maybe 3, like one for the Hemon, one for Rehovot, and one for the Eilat, or something like that. Right? I mean, the resolution stinks. It's like 10 miles or something, 15 miles or something like that. It's ridiculous, right? So therefore, they can't. The problem is they can tell you it's going to rain somewhere in the Sharon, right? But you don't live in the Sharon. You live in Ramat HaSharon, and you want to know you don't want to care what the weather is in Hod HaSharon. You want to know when it's going to rain in Ramat HaSharon.
he's actually living in.
Whatever.
Shut up.
All right. So yeah.
Is there any way to לשפר את הרזולוציה?
Yeah, if you have, the more billions you throw at it, you can improve it by a factor of 2. It costs $1 billion to put out, to do the measurements we have today. You spend another $1 billion, which of course I know you have, and you want to give it to science, right? After you tech exit, right, and you have nothing to do with your money, so you're going to give it to science, and they'll double the thing. And the problem is, however, it'll improve the forecast, first of all, the spatial resolution, so maybe they'll be able to tell the difference right? Something like that. Yes. But then in terms of the day prediction will get better. The 2-day prediction will get better. What Lyapunov exponent tells you is it doesn't matter what the hell, how many billions of dollars you spend on this problem. 2 weeks in advance, there's nothing you can say. Nothing. Basically nothing. And all the predictions for 2 weeks ahead are based on history of what has been the weather on July 13th for the last 30 years. Let's take an average. That's the answer, right? That's the level at which we do weather prediction long term, right? And just
So why do you even research in the field of climate physics if you can't say anything 2 weeks?
I think it was Kohelet who said, "Of the making of books, there is no end. Of the making, you can always do research. The fact that you can't answer the question that they're being paid to answer, that's your problem. That's not their problem. Right? I mean, you can answer the questions that God lets you answer, and it turns out that weather prediction after 2 weeks is something that God doesn't want you to know. There's no way of knowing." That's the way the world works, That's too bad,
every particle in
right? I mean, it's just too bad, but it's the way the world is. I mean, you just have to face facts.
How do you count the particles in Earth? Just count one by one.
So anyway, okay, where are we? Okay, so that's the Lyapunov exponent, and now, so really, and what distinguishes this from a single regular stupid instability is. What you really, if you do this for this initial condition and take two points, small, slightly separated here on the attractor, you'll get a Lyapunov exponent. If you do it here, you'll get a different Lyapunov exponent. If you do it here, you'll get yet another one. And so there's a spectrum of Lyapunov exponents, and what you're supposed to do is, in fact, average it over the entire attractor. And that's distinguishes it from a simple unstable fixed point where there's one number that characterizes the blow up of the things around, but then they go to some stable fixed point. I mean, there's one number. Here there's a whole spectrum of Lyapunov exponents along the attractor, and there's a distribution and blah blah, and you can spend a lifetime studying questions like that. But you need to know the concept of the Lyapunov exponent. Okay. Now there's okay. So, in fact, you can play the game more, just more pretty pictures. There are all kinds of bizarre things that happen. So, in fact, if you draw the bifurcation diagram, right? The bifurcation diagram, we said that R equals 1. Here, the 0 was their single global stable point, and then here we had our thing here, and then here's the hot RH, and then these end because they become unstable, and then, however, there's more stuff that's going on because there's a structure that goes like this, which is there is a associated with the hot bifurcation, right? There is a limit cycle, but it's an unstable limit cycle, and you could find it if you work hard, right? And that's
if you will try enough,
right. And that unstable limit cycle goes down. This is around for the standard parameters. There's a standard parameters. I forgot to mention this. Everybody who does everything there's a lot of parameters here. So they chose one set of parameters, which is the ones that Lorentz chose to begin with. Here. The standard parameters are sigma equals 10, b equals 8 over 3, 8/3. And now we're looking at things as a function of r. These kept fixed, because that's what Lorentz chose.
Why?
You have to ask Lorentz.
Where is his grade?
I don't know. Good question. All right. So anyway, you have this stuff.
Let's use a Ouija board.
And so here, this number here for those parameters is 24.74. This is 13.926. All right. And so what happens is, so here you have just the only thing up to here, the only thing you have is the two stable fixed points, right? And then one unstable fixed point. Now, starting here, it gets very interesting because you have a phenomenon that's called transient chaos, which means it looks like it's chaotic, and then it says, oh, what the hell, I'm going to go to a fixed point. So here's an example of that. You see, you start getting what's called the Lorentz butterfly, but in the end of the day, it says, I'm going to stop jumping back and forth. I'm just going to stay here and cycle into the fixed point. Into the limit. No, this is cycling down to zero, because here we're in the region where this point is still stable. There's still a stable fixed point here, right? In the region of transient chaos, there's still a stable fixed point to go to, and so it actually goes to the stable fixed point. It just, in the meantime, it decides to be a little chaotic along the way, just for the hell of it. All right? There's another beautiful picture here.
Yes, all the physicists that
Right. Where's the other picture? All these pictures. Well, I don't see it. Anyway, beyond, okay, all kinds of other things happen. So there's a region here, you get chaos, and actually there's a region of overlap where you have both the stable fixed point and the chaos coexisting. Because this is like a backward bifurcation, the hop bifurcation like backward, except the hop is chaotic. So therefore here in this region of parameters, you actually have a stable fixed point coexisting with full-blown chaos. And depending on the initial condition, you either will, if you're close enough to the fixed point or whatever, and everything is extremely sensitive to where exactly the initial condition is. Some things become chaotic, some initial conditions go to the fixed point, and who knows what. All right. And then all of a sudden, there's a region in R, there are a couple of regions in R which actually have periodic motions, have limit cycles. Just a small region in R, like between 19 point, I forget what the numbers are. And then eventually you get stable oscillations. When R is bigger than like 450 or something, you get a stable oscillation. But it's not an oscillation like this, it's an oscillation like that or something like that, some crazy oscillation.
You don't want to live in Earth that have this oscillation.
Yeah, right. So anyway, now, so what is the last thing I want to say is the other last thing that Lorentz did, which is the sort of the introduction to next week's lecture, is what's called the Lorentz map. So Lorentz asked himself, is there anything that I can say, any predictions one can make? You have this horrible thing or beautiful thing, whatever you want to call it. Can you say anything about this problem?
Eventually you will cry. But,
so he stared at it for 6 months or 8 months or whatever, and he came up with this brilliant idea. He said, let's look at so Z, if you look at Z, it oscillates. Because because Z goes up and here, Z goes up, right? It's circling, right? So Z is oscillating, but every time it comes around, it has a different value. So he said, let's look at the local maxima of Z. Right? Sort of the amplitude of the oscillation, if you will. It's one way of measuring the amplitude of the oscillation, right? So we're going to focus on Z max, the maximal Z's. The local maxima, right? Whenever Z went up like that, this point, right? So we have, look at the set Zn, which is the maximum of Z's. And then he plotted Zn plus 1 as a function of Zn. And he got the most amazing picture.
What is N?
The nth, you collect the series of data, right? And you have a series of 1,000 maxima. And now you plot Z, and for each point, you plot Z and the Z after it. The question is, does this current Z predict the next Z? Right? If I know how high it got this time, Well, I know how high it gets because it's basically getting bigger for a while, and then it goes over and then has to do something on the other branch, right? So for a while, it's just increasing. And then it gets too big because there's a limit. So it says, the hell with this, I'm going to go to the other side and start the game all over again.
What's the limit for the too big? You said there's the limit.
Well, the size of the attractor.
No, what did?
Oh, whatever the number.
Who cares?
It depends on the.
Yeah, I mean, no, it depends on the parameters. There's some value for this thing, but I don't know what it is. He didn't even put in the number, so I don't know. It's about here. No, this is, you don't see Z here, so I can't tell you. Anyway. Oh, here's the final. This is the final state when R is very big. You see beautiful periodic oscillations.
Yes.
Right. So when R is very big, and then you can do some analysis for R very big. It's not very interesting, but you can do it anyway. So you can write a paper about it.
And not receive another.
Now, where is my last picture here? The key picture. So what this thing looks like is the following. So what you see in this graph, so this is Zn, this is Zn plus 1. This line is Zn equals Zn plus 1, right? Which would be, if Zn equals Zn plus 1, it would be like a fixed point, right? And, all right. So what happens is, this is, I mean, it doesn't look like it, but this is a lot of points. And what's amazing is it looks like a curve, right? It looks like the following curve. I mean, here's the straight line. This starts here, it goes up, and it has a cusp, and then goes down again, right? And now it's true that this is not a real line. If you look with your microscope, and you look carefully, there's some scatter of the points. But on the picture, you see that you can't hardly see any scatter. So in other words, if you know Zn, you could predict what the next Zn is to within 1%. That's amazing, right? I mean, why should that be? But that's the way, and it works. And so what happens is you start here with some small Zn, right? And you see that the next one is a little higher, so you got a little bigger. And then you go across and you go up again, and it's a little bigger. You go across, up again, it's a little bigger. Gets bigger, 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 bigger. And then you go across, and then you shrink. And then you go across, and you go up again. And then you go across, and then who knows what, how. You can go up here and then down. And it goes crazy for a while, jumping back and forth. Right? Those are the, right? And then eventually it settles down again and goes up smoothly. And so this picture is an amazing encoding of something that's happening in the system, right? Which you can't predict at all. I don't think there's any theory of this curve at all. But somehow it's true, and it's not 100% true because it has a little width. It's got. But how would you even, what kind of a theory, could predict such a thing? Yeah?
It's like Julia said, that you have to take the last point to make the other one.
Right. Right. Well, yeah, and that's, in fact, right. So this idea, however, leads to the subject of next time's lecture, which is the dynamics of maps. Because this is the Lorentz map, it's a mapping from Zn to Zn plus 1. You can fit this to some curve, but it's not, you can do whatever. But it would be nice if you could predict that out of the equation somehow, other than just doing a long numerical, simulation, which has no insight. But I mean, the fact that he was able to see this in his head, that such a thing exists, is unbelievable. So you have to bow down to his amazing abilities to do, but we have no deeper understanding of this at all. But anyway, it inspires us to look at dynamics of maps because those are much simpler. Because once we reduce the dynamics to that of a map, then you can say things.
Now we can do math, right?
Right, then we can do some math problems.
Why it's not Gaussian?
Because why is it anything? It shouldn't exist.
No, you draw the linear line.
What?
You
very
draw the linear line. You not draw the Gaussian.
This thing is not a Gaussian. It's got a cusp here. What kind of curve is that? I don't know.
Should be a
It looks
Gaussian.
like a Gaussian.
No, Gaussian looks like this, my friend. That's a Gaussian with a nice rounded top and yeah.
If you take n to infinity, it becomes like a smooth curve.
No,
No,
it has a width. It has a finite width, so you can only predict within a percent or a half a percent.
but עדיין יהיו חורים כאילו בין נקודה גם כשאין לך.
I don't know. I didn't try. I've never tried. This
Does
is
it
the,
converge?
You- I don't know whether the Mitargelet is going to give you this as a homework, but if she was me, if I were her, or whatever the expression is, right? This is a beautiful numerical experiment you can do in the privacy of your, bedroom,
The one that do numeric.
right? Because all you have to do is integrate
A million.
to time t equals 1,000,000 and read off.
Will it converge?
Well, as I said, it looks to converge to something. Yes.
Okay.
Right. I mean, it looks to converge to something which is some, like the width of the touche kind of thing,
Yeah. Okay.
but what it really means in life, nobody knows. But so anyway, the point is that chaos. So this was the totally unexpected. This came out of left field. As I said, Landau had said nothing interesting happens in 3 dimensions and above. Eventually, mathematicians were able to prove that it can happen in 3 dimensions and above. Right? So once they knew the answer, that's like mathematicians, right? You tell them the answer, they can actually prove it, right? But they had no idea before that. But okay, that's fine. And Landau's physics intuition was completely wrong. But that's okay too. And it came out of nowhere. But people it was sort of like an underground activity. It wasn't really. It was a curiosity. And then once we moved to the maps, then it exploded. I mean, literally exploded. Front page of the New York Times and things like that. And then by now, it's again, there's 15 people in the world, or 150 people in the world working on chaos, right? And it's because there's a limit to what you can say. And they they sort of gotten 99.9% of what you can say, and the rest of the people were knocking around, working very hard at trying to get, whether there's something more there that we
Have to breathe.
But so the amount of papers written on chaos went from a couple of years, grew super exponentially for 5 years or 6 years, and then just as quickly.
Sound very dynamic.
Did it look like discussed?
Yeah, it looked like that cusp exactly. In fact, that's another good exercise, is to look at the number of papers on chaos. As a function of time, it probably reproduces the Lorentz thing.
Maybe
in
we
5 decimal
can
places.
say something smart when it
Right.
will.
So anyway, so that is the beginning of the story of chaos, and so next week is to talk about the dynamics of maps, which you can actually say something about, because this is all that basically people know about the Lorentz problem, and it's really hard. Other than it's really hard, which we know at this time. But all right, so that's all for tonight, and we'll pick up the story next week.
Thank you.
Yeah.
זה פרק 10.
This is the first of the ones on chaos. The 4 chapters at the end on chaos. The one this is called the Lorentz system or something. The word Lorentz.